All right, so good morning, everyone, and welcome to Lecture 18 of 124103 Biophysical Principles. In this lecture, we're still talking about heat. This is the last lecture on heat, and in this lecture, we'll discuss heat transfer by radiation. So we've started the series of lectures on heat by defining what temperature is, it's how hot or cold an object is. And we've seen that the hotter the object, the faster the atoms are moving, and that causes the object to expand. And and then we learned about heat being the energy that an object can gain or lose that results a change in its temperature or a change in phase. And last time we talked about two mechanisms for heat transfer by conduction. That's when the atoms in the object vibrate, and as they vibrate, they collide with neighboring atoms, and as they collide, they transfer some of their heat, and that's how heat is propagated by conduction. And the second mechanism for which heat can be transferred is convection, which is the mass movement of particles. And as these particles move about, they carry with them heat to different areas where they're moving to. So the third kind of heat transfer is is called radiation. And that's the topic for this lecture. So hopefully at the end of the lecture, we will be able to describe how heat is transferred by radiation. And in the first place, define what is radiation. We'll also learn about the radiation curve, which tells us how an object's property affects the amount of heat that is transferred by radiation. And then we'll tie up all the parameters in an object that affects the amount of heat transferred by radiation by looking at what is called the Stefan-Boltzmann's law. Okay, all right, so to understand radiation and transfer of heat by radiation, we again have to look at the microscopic scale. We again have to look at the atoms that make up an object, right? So everything is made up of atoms, and in the atom you have positive and negative charges, right? Electrons and protons. So let's consider an object which is made up of atoms, and you have electrons and protons in that object. So this is just in this illustration here, this is just an example of, it's just showing a pair of the charges, a proton, positive charge, and an electron, negative charge. These charges actually, they vibrate because nothing is frozen in time. So electrons and protons and atoms in a material or in an object, they vibrate. Okay. Yeah, so as they vibrate, so as these electrons and protons vibrate, they emit what is called electromagnetic waves. So that's the blue lines that are shown here. So these are the electrons that are in the material that vibrate, and as they vibrate, they emit what is called electromagnetic waves, which is this blue line here. And the electromagnetic waves, they propagate all throughout space. And as the electromagnetic waves propagate through space, they carry with them energy. Right. So the energy there is coming from inside the material, and it's propagated to the surroundings of the material via the electromagnetic waves that are generated by the vibration of the positive and negative charges inside the material. Okay, so that the the transfer of energy via the electromagnetic waves is what we call radiation. Okay, so yeah, so radiation, in short, is electromagnetic waves propagating through space, and as they propagate, they carry with them energy that's coming from the material. And because everything is made up of atoms, and everything is therefore emitting radiation. Okay, so thermal radiation is emitted by everything, because everything is made up of atoms. Yeah. And so how much radiation is emitted just depends on, for example, the temperature of the object, because we've learned previously that the hotter the object is, the faster the atoms vibrate. And the faster the atoms vibrate, the more electromagnetic waves are emitted, and therefore more energy is transferred, meaning more radiation is emitted if the object is hotter, so that the atoms vibrate faster. And so if here are two examples of thermal images of materials. So red sections mean that the material is hot, and the green section, bluer and greenish sections, mean that at that point the material or the object is cooler. Okay, so at the points where you have these red sections, that means the atoms vibrate faster at this point, and therefore they emit more energy via the propagation of electromagnetic waves. So radiation can also propagate through vacuum, through space. You don't need physical contact, or you don't need a medium for radiation to propagate through. And that's how heat is transferred from the sun to the earth, for example. The sun, of course, we know is very hot, so it emits a lot of electromagnetic waves. And those electromagnetic waves can propagate through vacuum, through space, and that eventually reaches Earth. And that's how heat is transferred from the sun to the Earth. So as opposed to heat transfer by conduction, so heat transfer by conduction, we also looked at the atoms inside the object. But heat transfer by conduction, you need physical contact so that the atoms can collide with neighboring atoms in maybe another object. And it's via the collision of the atoms that heat is transferred by conduction. But heat transfer by radiation, it's the propagation of the electromagnetic waves that transfers the energy from one point to another. And electromagnetic waves can propagate through space, through vacuum, and so you don't need physical contact. So that's the main difference between heat transfer by radiation and by conduction, right? So different properties of the object will influence how much heat is transferred by radiation, and that is given by what we call Stefan-Boltzmann law. But before we look at the equation, Stefan-Boltzmann's law essentially is an equation that brings together all these factors that affect the amount of heat that's transferred by radiation. Let's try to think about these factors in a more practical or logical sense. So practically, the amount of radiation that's emitted can be affected by the object's color. So in general, the darker the color is, the more absorbing it is. Okay. So for example, a black object will absorb more energy compared to lighter object. And animals sort of manifest this through usually animals who have lighter fur stay cooler compared to animals who are darker colored. And the effect of color on the amount of heat that's absorbed or emitted via radiation is described by this property called emissivity, which is described by this small letter E. So it's just a normal small letter E that we use to represent emissivity. But emissivity is a property of the material that describes its effectiveness to emit radiation, emit radiation. But emissivity has a specific value that goes only from 0 to 1. Okay? So 1 means it is very effective in emitting radiation, and an ideal object where emissivity is equal to 1 is called a black body. So a black body is an ideal or a perfect emitter. So it meaning it emits radiation 100%, and it also absorbs radiation 100%. Yeah, it's an ideal emitter of radiation. Yeah. So objects. So in the previous slide we said that darker objects, they absorb and emit radiation more efficiently than lighter objects. So darker objects, they have emissivity values close to 1. So black or very dark objects, we can approximate the emissivity of those objects to be close to 1. And that means that they are very good in emitting radiation, and therefore they easily lose energy via radiation, but they can also easily gain energy by absorbing radiation as well. The opposite side of the spectrum, for zero emissivity, these are for objects that are highly reflective, like shiny metals. Okay, they reflect all of the radiation that arrive on their surface, and therefore they almost do not absorb any energy. They also cannot emit energy by themselves, but instead they just reflect energy that arrives on their surface. Right. So emissivity, it's a constant number that is a property of different objects. So usually we'll either give you the emissivity, or you can look it up in a table, or you can Google what's the emissivity of this color or of this object, for example. Right, so the amount of radiation also depends on the area, the surface area. Yeah, of course, the larger the surface area, the more radiation can be emitted, right? Because the larger the surface area, you can imagine going back to the very first slide where I showed the electrons and protons that are vibrating and that are emitting these electromagnetic waves that carry with them energy. So you can imagine like a larger surface area having, more atoms that are vibrating and exposed to the environment, then you can have more electromagnetic waves emitting from a larger surface area. Yeah, and that also, we can also observe the difference in surface areas in animals. So animals who live in very hot climates like the desert, they usually have very large ears. If you see elephants in in the desert, compare that to elephants. So elephants in Africa, for example, compared to elephants in Thailand. Africa is much hotter, so the elephants there will have larger ears compared to elephants in the cooler climates of Thailand, for example. And the larger surface area allows the animals to lose more energy via radiation, and that helps in cooling down their bodies and prevents overheating, especially during very hot weathers. Okay, so very large surface areas contribute to larger heat loss via radiation. The amount of radiation emitted by an object is also affected by its temperature. So the hotter the object is, the more radiation is emitted. And again, we can understand this by looking at the very first slide where you have there the vibration of the atoms. And as the atoms vibrate, they emit the electromagnetic waves that carry energy via radiation. So we've learned that the hotter the object is, the faster the atoms vibrate. So the faster the atoms vibrate, the more electromagnetic waves they emit. And the more electromagnetic waves they emit, the more energy is carried away from the material. Yeah. So the hotter the object, the more radiation is emitted. So there's a question there, any examples for emissivity is equal to 0? So silver will be a good example for, for example, silver, you know how one of the things they say you should have in your first aid kit is a thermal blanket. The thermal blanket essentially has a silver lining to it, and it keeps you warm. So if you put on the thermal blanket which has this silver lining, silver is highly reflective. It has emissivity that's close to 0. And yeah, mirrors essentially is just glass that's coated by aluminum or coated by silver, and it's the silver and aluminum coating that makes mirrors highly reflective, and the high reflectivity of these things prevent the body from emitting. So when the body still continuously emits radiation, right? But then if you have this silver highly reflective blanket around your body, the high reflectivity will just reflect the heat generated by the body back to the body. So the blanket, instead of absorbing the energy emitted by the body, the silver blanket will reflect all of the energy emitted by the body, and therefore that keeps the body warm. Because instead of absorbing the energy emitted by the body, the silver blanket with emissivity close to 0 reflects all of the energy back to the body. So mirrors, mirrors essentially they're coated with aluminum or silver. So aluminum would also be a good example of something, an object with emissivity close to 0. So think about highly reflective objects. They will have emissivity close to 0. And black will have emissivity close to 1, and anything in between will have emissivities that's between 0 to 1. Good. All right. So surface area, temperature. Okay, we've also already talked about temperature. The hotter the object is, the more radiation is emitted, because the faster the vibration of the atoms will be, and therefore the more electromagnetic waves are emitted, the hotter the temperature is. So the the effect of temperature on the amount of radiation can be observed via what we call radiation curves. So radiation curves, these are examples of radiation curves. So the green, orange, and red curves in this graph, they are the radiation curves. It tells us the intensity. Intensity is essentially the amount of radiation. So how intense the radiation is, and then the y-axis is what we call wavelength. Well, a wavelength is a characteristic of the wave, and we haven't really still talked about waves and wavelengths. This is the topic for next week. Actually, next week we will talk about waves and wave and the properties of the waves, and one of the properties is the wavelength. So we'll talk more about wavelengths in the next lecture. So I'll just try to discuss radiation curves in general terms. So radiation curves just gives us a relationship between the temperature and the wavelength of the electromagnetic wave. So notice here the green curve that has a temperature of 6,000 Kelvin. Orange curve has a temperature of 4,500 Kelvin, and the red curve has a temperature of 3,000 Kelvin. So that means different temperatures. So hottest is the green curve. You can see that the hotter the object is, the higher the temperature, the more intense the radiation is, right? So intensity is the y-axis. Notice how the green curve is more intense. It has a higher intensity compared to the red curve. The red curve is colder compared to the green curve. Okay. What we can also see from the radiation curve, aside from the intensity, is how the intensity of radiation shifts according to the wavelength. Wavelength is related to the color of the object that we see. So maybe let's just look at the visible. So the visible wavelengths, these are the wavelengths that we can see. These are the colors of the rainbow. So that means red, orange, yellow, Roy-G-Biv. Essentially, a particular color has a particular wavelength. So blue is around this. Blue has a shorter wavelength. So you go from 0 wavelength to 3,000 wavelengths. So you're going from left to right, you are increasing the wavelength. Blue is around this point, and red is at the extreme ends of the visible spectrum. So that means blue has a shorter wavelength compared to red. So blue, shorter wavelength, and red has a longer wavelength. Right. So what this radiation curve tells us is, if you notice at the notice the peak. So the peaks of the radiation curves are these ones. Peak meaning the highest intensity. So for the green radiation curve, the peak is around here with that wavelength. For the orange radiation curve, the peak is around that point. For the red radiation curve, the peak is here. So notice how the peak, the position of the peak shifts from short wavelength to long wavelength. So going here from on the left side of the graph, short wavelength, and the long side of the graph, far right side of the graph, you have long wavelength. So the green radiation curve has the peak of the green radiation curve is at a shorter wavelength compared to the peak of the red radiation curve, right? So what we can see from the radiation curve is that The shorter the wavelength is, the higher the intensity of the radiation, meaning the shorter the wavelength is, the more, the higher the amount of radiation that is emitted. Okay. So going back to blue and red, blue has a shorter wavelength compared to red. Okay. So that means which color, blue or red, will have a higher amount of radiation, a higher intensity for radiation. Is it blue or red? Blue, yeah. Okay, yeah, blue. You're correct, Nikita. So blue has a shorter wavelength compared to red. Therefore, blue should have a higher intensity radiation compared to red, meaning blue, the amount of radiation emitted by a blue object will be higher compared to the amount of radiation emitted by a red object. Okay, so maybe you've heard, maybe you know, or maybe you've heard the saying that blue flame is hotter compared to red flame. And this is the reason behind that observation. Yeah, yeah. Maybe you've heard that, or you've read that, or at some point, or maybe you know that blue flame is hotter than red flame, and this is the whole reason behind that observation. So blue has a shorter wavelength compared to red, and the radiation curves tell us that the shorter wavelength will emit more radiation compared to the longer wavelength, and therefore blue objects emit more radiation compared to red objects. Okay, so that's the basic concept behind radiation curves. We from the radiation curves, we can observe two things. Okay, the higher the temperature is, the more radiation is emitted. And the shorter the wavelength is, the more radiation is emitted. So those are the two things we can get out of radiation curves. And I guess for now, that's just what we need. We will, without talking much about what wavelength is, because we'll talk more about wavelengths and waves in the next lecture. Okay. All right, so far we've seen the amount of energy emitted via radiation depends on the color, the emissivity of the object. It depends on the area that's emitting radiation, and it depends on the temperature, of the temperature of the object. So if we put all of those factors together, we have what we call Stefan-Boltzmann law. Okay. But before we go to Stefan Boltzmann's law, there is this good video actually, that illustrates radiation. So this video shows you a thermal image of an object, and the thermal image sort of shows you how heat is lost via radiation. So watch this video, and let's see if okay. So let me figure out the sound. Let's try that again. The sound's not working. Let me see. Okay. This was working earlier. Let me just stop sharing for a moment and can you hear the sound now?
We're here at Mar Lodge in the Cairngorms in the Eastern Highlands of Scotland
Yep.
for Winter Watch.
Let me just start that. All right. Yeah. Okay, good. So that video showing you the heat loss via radiation. If it's also a windy day, for example, then there will be, you can have several heat loss mechanisms occurring all at the same time, right? So if it's a windy day, you can also have heat loss via convection, as the air molecules will take away heat from the surface of the skin. So you have the heat loss by radiation. Heat loss of radiation sort of is always present, because as we've said, all objects have atoms, and the atoms, they're always vibrating. And so heat loss by radiation will always be there, regardless of whether you have an environment, an atmosphere around you or not. And if he holds the ice, you can also have heat loss by conduction, because then part of the heat from the body will transfer to ice or something. If he holds something cold, then you also have heat loss by conduction in that case. Yeah, so I think this video is a good illustration of the different heat loss mechanisms that can occur all at the same time. Right, but focusing again on the heat loss by radiation, and we've seen the different factors that can affect heat loss by radiation. We can combine all of those in an equation called the Stefan-Boltzmann's law, or simply Stefan's law. Okay. So the amount of heat lost by radiation as the object radiates, it's given by this equation. So first, let's just consider the object that's by itself. We won't consider the effect of the environment. It's just the object by itself. So the object is radiating. So you have radiation coming from the object. We've seen that it depends on the color of the object, the emissivity. So E here is the emissivity of the object, and emissivity has no units. So the higher the emissivity, the more energy is lost by radiations. But of course, emissivity is just from 0 to 1. So it's just from 0 to 1. The value of emissivity is just from 0 to 1. The maximum you can have is 1. And if emissivity is equal to 1, that means you have the maximum amount of heat loss by radiation as a factor of the color or emissivity. We've also seen that it depends on the area. So A is the surface area of the object. Okay? The bigger the area that's exposed, the more energy is lost by radiation. So there's a direct proportionality between area and the amount of energy lost. It also depends on temperature. So we've seen that the hotter the object is, the more energy is radiated the higher the amount of energy lost by radiation. So temperature T. A very important thing to note when you're using this equation is that the temperature should be in Kelvin. And so I've written here absolute temperature. Absolute temperature means that the unit for the temperature must be in Kelvin. So there's no getting around using Celsius in this case. So in the previous heat transfer mechanisms where we were getting the difference in temperature, right? Delta T, T hot minus T cold, we didn't care so much whether the temperature was in Celsius or in Kelvin, because when you subtract two temperatures, the resulting temperature in Kelvin is the same as in Celsius. But for heat transfer by radiation, it's not a temperature difference. It's just a temperature by itself. Okay, and so the temperature must be in Kelvin. It should be the absolute temperature. And the main reason why the temperature has to be in Kelvin is because of this constant called the Stefan-Boltzmann constant, given by the symbol which we read. This is a Greek symbol called sigma. Okay, sigma, the Greek symbol, sigma is called Stefan-Boltzmann constant. It's a constant number that's equal to 5.67 times 10 to the minus 8 watts per meter squared per Kelvin to the power of 4. So it's a constant number and it has a unit in Kelvin. And therefore, the unit for your temperature must be in Kelvin as well. Okay, so that's something very important to take note of. Remember to convert your temperatures to Kelvin when you're using this equation for radiation. Okay, so the amount of radiation depends on the emissivity. It's proportional to the emissivity. It's also proportional to the area, to the temperature, and of course, it should be proportional to the time. So small t is the time, don't have it here. Time of exposure. So of course, the longer you are exposed, the more energy is lost by radiation, right? Okay, so that's the time t. If we divide both sides by the time, like we did in conduction and convection, so if you divide both sides by time, we will have Q over T, and time disappears on the right-hand side. But we have, again, the rate of heat transfer or rate of heat loss by getting Q divided by the time T. Okay. The rate of heat loss is, again, just depends on emissivity, temperature to the power of 4, the area, and the constant. Okay. So you use this equation if the object is just by itself and the object is just emitting radiation by itself without considering the atmosphere or the environment where the object is. But of course, the object will always have a surrounding environment, right? So we have to also consider the surrounding environment of the object. And so the total rate of heat loss from an object is given by this equation, where we now consider the effect of the surroundings or the environment. So a way to understand this equation, you see you have this E times sigma times A being multiplied to this bracket here. And we said that if you have this factor multiplied to a bracket, we can distribute that factor to each term of the bracket. So we can expand this equation as like this. Right? Distributing this term to each part of the bracket, we can expand that equation into this form. The first equation, the first part of the equation, we've seen that in the previous slide. This is the heat lost, heat emitted by the object to its environment. And the second term is the heat absorbed from the surroundings. Okay. Right. So the total heat lost is a combination of the heat emitted by the object minus the heat that the object absorbs from its surroundings. Okay. And so you have there two temperatures. T is the temperature of the object. Okay. And T subscript S, you have the subscript S to tell you that's the temperature of the surroundings. Okay. Be very careful here. The temperatures, again, must be in Kelvin. Okay. Because although we are subtracting two temperatures, the temperatures have exponent 4. So it's not the usual temperature of the object minus temperature of the surroundings. What you need to do is you have to raise the temperature of the object to the power of 4. Also raise the temperature of the surroundings to the power of 4, and then you subtract those two. And because of the exponent for Celsius is not equal to Kelvin, even if we're taking the even if we're subtracting two temperatures. Okay, so you have to be very careful. The temperatures really must be in Kelvin, right? So usually it's this equation that we will use often because if you have an object that's emitting radiation, it will always have a surrounding environment, right? It will always have an atmosphere around it. Okay? And it's only when the temperature of the surroundings, if the temperature of the surroundings and the temperature of the object's the same, then you don't have any, the amount of heat emitted is equal to the heat absorbed, and temperature will not change. So, yeah. Okay, so let's look at an example to see how to use that equation, Stefan Boltzmann equation. So calculate the rate of heat energy radiated from a person. The total surface area of that person is 1.5 meters squared. The person is in the room. The temperature of the room is 22 degrees Celsius. The temperature of the skin, the person's skin, is 33 degrees Celsius. We're given that the emissivity of skin is 1. So yeah, right. So we were given explicitly that the heat transfer is via radiation. Another clue is you have emissivity. So that means, you know, heat transfer is by radiation. Okay. We're being asked to find the rate. So rate means heat divided by time. So it's the Q divided by T equation. And we have that here. Sigma, it's just a constant number, 5.67 times 10 to the minus 8 watts per meter squared per Kelvin to the 4. We can see that we have everything. So we have the area is equal to 1.5 meters squared. Emissivity is equal to 1. Temperature. Okay, what temperature will you put for T? Is it 33 or 22 degrees Celsius? The temperature for T. Just T. What is T equal? There are two temperatures given. Will T be 22 degrees or 33 degrees? Yeah. So T will be the temperature of the skin because it's that T is the temperature of the object that's emitting radiation. In this case, the skin is emitting radiation. So you have 33 degrees Celsius. And TS, that's the temperature of the environment, the surroundings of the object, that's 22 degrees Celsius. right? So you have to convert your temperatures to Kelvin. You have to add 273 to each of the temperatures. So 306 Kelvin and 295 Kelvin. But essentially you have everything. Okay, temperatures must be in Kelvin because sigma is in Kelvin. So just substituting everything, emissivity is equal to 1, sigma is constant, the temperature of the skin, don't forget you have to raise that to the power of 4 minus the temperature of the surroundings, you have to raise that to the power of 4 as well, times the area 1.5, and you should get 102 watts for the rate of heat transfer. All right. So I guess 2 pressure points in using this equation. The first one is make sure you convert your temperatures to Kelvin. Second one, don't forget to put the exponent for the temperatures. So once you converted your temperatures to Kelvin, get the raise that to the power of 4. In your calculator, you can use like EXP and then number 4. I don't know. I have this kind of calculator, the Casio one, that has the EXP function. And that's where you get the power of 4. All right. Are we happy with the solution to this question? Good. All right. Okay. So that essentially wraps up the discussion on heat transfer by radiation. Now I would like to talk about evaporation as a form of as a mechanism for heat loss. Okay. We've of course seen evaporation in the last workshop, but we'll talk about that more in detail. So evaporation is a form of heat loss. It's a heat loss mechanism that will result to cooling of the body, and that occurs due to the phase change evaporation. So evaporation is of course a form of a phase change. The sweat being converted, liquid sweat being converted to gaseous form. So here in evaporation, you have the heat released. So this side here, the left side of the equation, is the heat released by evaporating the sweat, translates to the heat lost by the object. All right, so in evaporation, you have, say, let's just use sweat because it's easy to imagine. So you have sweat on the skin. Okay? The skin will lose some heat, maybe by radiation or some other means, maybe by conduction. Essentially, the skin will lose some heat, and the heat lost by the skin will go into evaporating the sweat. Okay? When the skin loses heat, the temperature of the object will change, right? We've learned that if you lose heat, that results to a change in temperature for the skin, but that also results to the evaporation of the sweat. So you have here now the relationship that the heat that's released by evaporating the sweat will translate to the heat lost by the objects. Okay. We've seen those two equations, Q equals ML for phase change and Q equals MC delta T for, so you have Q equals ml for evaporation and Q equals mc delta T for the change in temperature. It's the same amount of heat because the heat used to evaporate the sweat is the same amount of heat that results to the change in temperature. And because Q is the same, we can therefore say that ml is equal to mc delta T. Right. Okay, so by understanding what's happening in evaporation conceptually, we can then understand that this mass cannot be canceled. So you can see in this equation, mass is on the left side and mass is also on the right side, but these are different masses. So the mass on the left side, this is the mass of sweat that evaporates. Okay. And the mass on the right side, this is the mass of the object whose temperature changes as a result of evaporation. Okay, so the masses are different. So mass on the left side, that's the mass of the sweat that evaporates. The mass on the right side with the delta T, that's the mass of the object whose temperature changes as a result of evaporation, of heat loss by evaporation. Okay. Right. So just before we proceed to an example, does this equation make sense? Because I think the whole, the key idea behind evaporation is essentially that heat lost by evaporation goes into changing the temperature. Okay, so let's look at this example to see, to sort of test our understanding. So the latent heat of vaporization of water, latent heat of vaporization is the latent heat that's involved in evaporation. So we give that the symbol L subscript V. So latent heat of vaporization at body temperature is 2.42 times 10 to the 6 joules per kilogram. And to cool the body of a 75 kilogram jogger with an average specific heat of 3,500 joules per kilogram per Celsius by 1.5 degrees Celsius, we want to know how many kilograms of water in the form of sweat must be evaporated to cool a jogger who is 75 kilograms. And we want to cool the jogger by 1.5 degrees Celsius. And we have here a choice of answers. Actually, I think this is a question from the exam in 2020. That's why there are like choices. It's a multiple choice question. All right, so let's try to dissect this problem. So of course the heat. So what we're going, we have to separate the two. There are two things here. There's the sweat that evaporates, and there's the jogger that loses heat, that changes temperature. So we have to sort of separate those two things. So you have the jogger. The mass of the jogger is 75 kilograms. The specific heat capacity of the jogger is 3,500 joules per kilogram degrees Celsius. Okay, and then you have there the temperature will change by 1.5 degrees Celsius. So that's the change in temperature is already given, 1.5 degrees Celsius. It's a change in temperature, so that's also equal to 1.5 Kelvin. Right. So that's all the information that's given about the jogger. Okay, about the sweat. Okay, what do we know about the sweat? Latent heat of vaporization of water. So we assume that the sweat is in the form of water. Right, so we can use the latent heat of vaporization of water, use that for the sweat. Okay. And we want, so that's the only thing that's given about the sweat. What we want to find is the mass of the sweat. Okay. And to distinguish the masses, I'll use subscripts. M subscript J will be the mass of the jogger, and M subscript S will be the mass of the sweat. Okay, right. So you have sweat that evaporates, goes into changing the temperature of the jogger, right? So you have, therefore, the relationship. The heat goes into evaporating the sweat, M subscript S, will translate to the change in temperature of the jogger, M jogger times C times delta T. Right? What we want is the mass of the sweat, M subscript S. So we rearrange this equation. So M jogger C delta T, rearrange to isolate MS. Okay. We can divide both sides by LV, and therefore MS is equal to mass of the jogger times specific heat capacity times change in temperature divided by the latent heat of vaporization. And we actually know everything. So we can plug in the mass of the jogger times specific heat, 3,500, times the change in temperature divided by the latent heat of vaporization. Okay. Gives you a mass of 0.163 kilograms. All right. And the recipe is sort of the same for any evaporation type of problem. It's really just the key idea that the heat lost by evaporation goes into changing the temperature. So that's the first key idea. The second, so that's the first pressure point, knowing that concept. The second thing is to realize that the masses are different. So the mass here will be the mass that of the thing that evaporates, okay? And the mass on the other side is the mass of the thing whose temperature changes. Right, are we happy with the solution to this example? Cool. Good. All right, so yeah, so evaporation, it's a mechanism for preventing heat, but mechanism of cooling the body by losing heat, and the heat lost goes into evaporating the sweat. So some animals are not able to sweat, okay? Because they have fur that cover their skin, so sweat from the skin cannot easily evaporate. They use other means to cool their body, for example, evaporation from the tongue, but essentially it's the same concept. You have, they hang their tongue out. The tongue has some, of course, liquid there, but it's the same concept. The saliva in the tongue will evaporate, so you have M times LV, and that results to the change in temperature, overall temperature of the animal. Okay. Alternatively, they roll over to expose the skin, which allows more heat loss. In this case, you could probably say that it's heat loss by conduction as the skin comes in contact to the cold ground, or it can also be heat loss by convection. As the skin is exposed, air can easily transport heat away from the skin. Okay. So yeah. Right. So this slide just shows us some different mechanisms that animals use, mammals use to in response to heat loss. So you can just read this slide. I'm not going to essentially read what's in here. I think they're pretty much self-explanatory and yeah, just explaining some mechanisms for which mammals respond to heat loss. Either they want to encourage heat loss when they're about to heat up, in which case, you know, it will be the opposite. Instead of constricting the blood vessels expand and the blood vessels sort of go close to the skin to encourage heat loss by convection and conduction. But when the mammals are cold, the blood vessels constrict so that to prevent heat loss by convection or conduction. All right. Yeah, so that ends our lecture on heat transfer and heat in general. Yeah, and we have the workshop. So do you have any questions about the lecture? Yeah. Before we go to the workshop, and I guess, but that ends the lecture. I'll just keep that. Before we go to the workshop, I'd just like to address something that, because I noticed that there's been a lot of discussion going on stream about lab, the next lab. What's this? Lab experiment number 4, where you investigated the pendulum. Either you investigate the effect of mass or the effect of the length of the string on the period of oscillation for the pendulum. I think I noticed there was some discussion there about question number 6 in the homework of lab number 4. Question number 6 says, what fraction of measurements are within the range and why are the results outside the range? Is that, yeah, is that right? Do you think that's something you want me to talk about before we go to the workshops? Yep. Okay. All right. So let's talk about that. So in the lab homework, you were asked to vary either the mass or the length of the pendulum, and then you get the period. So let's just say, just for discussion's sake, let's say that you chose to vary the mass. So for example, you had for example, mass 1, and you measured the period for mass 1. You measured several periods and you had like the mean or the average in mass. Yeah, that's the mean. For example, you obtained a mean of 2 seconds, just for argument's sake. Yeah, for example, so let's say, yeah, the mean or average period that you got was 2 seconds, and then the standard deviation that you've calculated in the period is 0.5 seconds. Okay, and say for the second mass, the mean that you got was, for example, 2.2 seconds, and say, for example, the standard deviation was 0.4 seconds. Okay, so these are just random numbers for the average and standard deviations of the periods that you obtained for different masses. So the mean and the standard deviation means that for the first mass, you have 2 seconds plus minus 0.5 seconds for your period. That means that the period goes from, so what this essentially means is that the period goes from 2 minus 0.5 seconds to 2 plus 0.5 seconds. So the range of your periods, is 1.5 seconds to 2.5 seconds. So that's the range of the periods that you had for mass 1. So similarly for mass 2, if you write this out, this is 2.2 plus minus 0.4 seconds. Okay. That means the period goes from 2.2 minus 0.4 seconds to 2.2 plus 0.4 seconds. Okay. And that will give you a range of 1.8 seconds to 2.6 seconds, right? So that's essentially what the standard deviation and the mean means. So that's why you want to get the mean and the standard deviation, is for you to determine the range of the periods given the experiment, that the parameters that you chose. So if you plot this, say if you compare this to and you say that's 2, for example, that's 2.2, 2.4, 2.6. What's our biggest one? 2.8. And then on the other side, you have 1.8, 1.6, 1.4, 1.2. Okay, so if you compare those two, for the first mass, you have a range of values of 1.5 to 2.5. So for the first mass, 1.5 to 2.5. Okay. Range of periods for mass 1 goes from 1.5 to 2.5. And for mass 2, the range goes from 1.8 to 2.6. So that means 1.8 is here and 2.6 is here. So you have here the range of periods for mass 2. Okay, so what question 6 is asking is, see what is the fraction of overlap, or essentially question number 6 asks you to sort of quantify the overlap between the two ranges that you have. Okay, so here you can see that there's more than 50% overlap between the ranges. So you can sort of estimate. So you can answer question number 6 several ways. You can say that the fraction more than there is greater than 50% overlap between the ranges. Okay, so you can say that there's more than 50% of the measurements in mass 1 overlaps with 50% of the measurements in mass 2, for example. And therefore, because there's a large overlap, then you can say that the periods for mass 1 and mass 2 are almost the same, and therefore mass does not affect the period. Okay. So if there's a large overlap, you can conclude that the periods are essentially the same. And it's just the variation in the periods is just an effect of the errors in your measurements. But if there's very small overlap, say, for example, your range of measurements sort of looks like this. Okay, so yeah, for example, the range of your measurements look like this. There's a very small overlap. Say, yeah, it's overlapping, but it's very small, say only 5%, only 5% of measurements are within this overlapping range, then you can conclude that the periods are different, and therefore mass should affect the period. Okay, so here, so the range of periods is 2.06 to 2.18 for mass 2, and 2.03 to 2.23. Yeah, so it's completely inside, right? So you can completely fit 2.06 to 2.18 completely fits inside 2.03 to 2.23. So the fraction of measurements is almost 100%. So almost 100% overlap. Yeah, so that, of course, that counts now as overlap. So here, this one is a small overlap. Here, in this case, it's a large overlap. In your case, Oksana, it's 100% overlapping, right? Because one range is exactly inside the other range. Yeah, so in your numbers, you can definitely conclude that mass does not affect the period because the periods are essentially the same. The range of values overlap. Yeah, and you can conclude that the periods are essentially the same within the errors of your experiment. So that's, I guess that's how you answer question number 6 with the fraction of measurements. You can just answer that by like estimating the amount of overlap in your ranges. Is it, yeah. All right, does that make sense? And I hope that clarifies the question and the discussion that was going on stream. Good. Okay. Great. So then